Hi guys, today I will tell you about the short description about the theoretical physics. What is theoretical physics and how to understand theoretical physics, and what is the role of theoretical physics in our daily life, and what is the future of theoretical physics basically. Theoretical physics is the attempt to describe nature quantitatively using the languages of mathematics. Indeed, there is an interplay between mathematics and the optical oriental physics, with both disciplines enriching each other's. Isaac Newton invented calculus in order to apply it to classical mechanics. Michael Faraday developed the field concepts in order to describe electromagnetism. David Hilbert's abstract space of square integrable functions turned out to be the home of quantum mechanical wave functions. Paul Dirac invented the alpha functions, which motivated mathematics to develop distribution theory. Abelian gauge symmetry was discovered as the basic principle underlying Maxwell's equations. Sophocles' abstract concepts of non-abelian symmetry algorithm and a symmetry group underlie Wolfgang Paulin's ideas about non-abelian gauge symmetry, which were further developed by Robert Mills and Chen Yang, and were late discovered to form the basis of the strong and electroweak interactions. Michael Atalian and Isidore Yersinger investigated the topological properties of Dirac operators, which turned out to be essential in the context of anomalous symmetries in quantum field theory, which are present at the classical level but cannot be maintained in the quantization process. Michael Berry realized that topological features of wave functions play a central role in adiabatic processes in quantum mechanics and can be characterized by abstract Abelian and non-Abelian gauge field in the space of slowly varying external parameters. This list could be extended much further, and the creative process of discovering new mathematics when thinking about nature or using existing mathematics to describe its observed behavior is likely to continue for a long time. In this course, we will familiarize ourselves with some advanced mathematical concepts that are at the basis of the modern theories of particles and condensed matter physics, as well as of some advanced topics in quantum mechanics. Although the subject is mathematical, we will by no means apply the rigor of mathematician. Instead, we will concentrate on those aspects that are most relevant in physics application. Consequently, we will avoid very abstract mathematical constructions in favor of a hand-on practitioner's approaches. While we aim in understanding the subject at a deep level, we will not attempt rigorous proof, and we will sometimes even limit ourselves to applying specific procedures. For example, when we produce products of SU representations without proving their validity, when we discuss Lie algebras and Lie groups, as well as the topology of the corresponding group manifolds, we will focus on those aspects that are most important in physical applications. A systematic mathematical exposition of those subjects would go far beyond the scope of the current courses. For example, the concept of the Killing vector field of a Lie group manifold is not developed, although it does have physical applications. Although the present material is neither mathematically rigorous nor complete, it will hopefully provide the reader with a solid basis for better understanding the quantum field theories that underlie modern practical particle physics as well as some theories in condensed matter physics. It is a most fascinating aspect of physics that on all length scales nature can indeed, by describing mathematically the most fundamental building blocks of matter, elementary particles such as electron and proton as well as quarks and gluons are precious embodiments of abstract mathematical concepts. Even on much coarser length scales, the plateaus in the resistivity of a quantum Hall sample are most precious, quantized in units of Planck's quantum and the elementary electric charges. Even the evolution of the entire cosmos is controlled rather preciously by the differential equations derived from general relativity, assuming the Friedman Letman Robertson water metric, as I argue in an appendices to these lecture notes. It is the locality of space and time and the existence of vast hierarchies of distance scales that leads to the success of physics and thus explains why physics exists. In this course, we will familiarize ourselves with some important advanced concepts of theoretical physics in order to be better prepared to understand the modern theories of particle and condensed matter physics as well as some aspects of advanced quantum mechanics. This may even inspire us to invent our own new mathematics or to be creative when trying to describe some new aspects of nature mathematically. Mathematics is a universal language spoken by curious minds and capable brains and used for various purposes, in particular to communicate the abstract beauty of nature. Let us learn more about this language and let us keep in mind that theoretical physics is a man and woman made endeavor that relies on our curiosity as much as on our mathematical capabilities. So thank you so much for listening. I will tell you some more discussions about this description about the application of theoretical physics in the field of mathematics in our daily life. So thank you so much again.